Question number 31. Which of the following is used for the correction of short-sightedness? A. Concave lens, B. Concave mirror, C. Convex mirror, D. Convex lens. Now the correct option here is concave lens, because concave lens is a lens used for correcting myopia, which is another name for short-sightedness, while the convex lens is used for correcting hypermetropia, which is a long-sightedness. So option A is the right answer. I hope that answers the question. Question number 32. Dispersion occurs when white light passes through a glass prism because of the A. Different speed of the colors in the glass, B. High density of the glass, C. Defects in the glass, D. Different hidden colors in the glass. Now, what is dispersion? Dispersion simply means the splitting of light into different colors as it passes through a glass prism. Now, the glass prism almost has nothing to do with the dispersion. It is the light itself that causes this dispersion. But the glass prism is just used as a medium to make this dispersion happens. So if we look at option D, it says different hidden colors in the glass. The glass has no colors in it. And then option C says defect in the glass. The defect in the glass does not affect the dispersion. And then option B says high density of the glass. Whether the glass is having a high density or a lower density, dispersion always happens. And then option A says different speeds of the color in the glass. Now the speeds in which this light carries, in which different spectrum of this light carries, is the reason why this dispersion happens. So option A is the final answer. Different speeds of the colors in the glass. I hope that answers the question. Now question number 33. When a positively charged rod is brought nearer the cap of a positively charged electroscope, the leaf divergence will. Now the positively charged rod, now the rod is positive and the electroscope is also positive. So when the rod is brought near the head of the electroscope, what happens to the leaves? Now the leaves are going to converge because the rod is positive and the electroscope is also positive. So you see the leaves moving towards each other. Now that movement they have towards each other is a form which we call convergence. Now they are converging together, which makes option A the final answer. A converge, B remains constant, C diverge, D be induced. I hope that answers the question. Question number 34. 3 capacitors of capacitance 2 microfarad, 4 microfarad and 8 microfarad are connected in parallel, and the potential difference of 6 volts is maintained across each capacitor. The total energy stored is, now the total energy stored in capacitors E is given as CV squared all over 2. Now these capacitors are given to us. We have 3 capacitors given to us from this question. We're going to take these data out. We have C1, the first capacitor is 2 microfarad, and C2 is 4 microfarad, and C3 is 8 microfarad. Now the total capacitance of a capacitor that is connected in parallel is simply, we just need to add the capacitance together. So the total capacitance C is equal to C1 plus C2 plus C3. But if I want to get the total capacitance here in the circuit, I need to add these capacitors together. This is the same thing as C1 is 2 microfarad plus 4 microfarad plus 8 microfarad. If I add all this together, 2 plus 4 is 6 plus 8 is going to be 14 microfarad, and the symbol here, micro, stands for 10 to the power of negative 6. So C is 14 times 10 to the power of negative 6 farad. Now if we've gotten this, we're asked to calculate the energy that is stored. Now the energy from the formula above, and the potential difference was given to us in the question, that is V is equal to 6 volts. Good. So it was given to us to be 6 volts. Now if I substitute these values into this formula above here, the total capacitance is 14 times 10 to the power of negative 6 farad times the V is given to us to be 6 squared all over 2. And when we carry out this, we multiply this by 6 squared, which is 36, we're going to have 2.52 times 10 to the power of negative 4 joules. So now the energy is 2.52 times 10 to the power of negative 4 joules, which makes option C the right answer. I hope that answers the question. Question number 35. A cell of EMF 12 volts and internal resistance 4 ohms is connected to an external resistor of resistance 2 ohms. Find the current flow. A says 4 amps, B says 2 ampere, C says 3 ampere, and D says 5 ampere. Now, the current, if we are calculating the current here, the current is equal to E all over R plus R, where I stands for the current, and then E is the EMF, and then the capital R is the external resistance, and the small r is the internal resistance. Now let us bring out the data. Now the data says a cell of EMF E is given to us as 12, and then we have the internal resistance given to us as 4, and then we have the external resistance from the question given to us as 2, and then we're asked to calculate the current. Now if we substitute these values into these formulas, it is going to be very, very easy for us. Now I is equal to E, which is 12 divided by the external resistance, which is 2, plus the internal resistance, which is 4. So if I have this, I'm going to have 12 divided by 2 plus 4 is 6, and 12 divided by 6, the current is equal to 2 amps, and then which corresponds to option B. Option B is the final answer. I hope this answers the question. Question number 37. 3 4 ohms resistors connected in parallel have a potential difference of 16 volts applied across them. What is the total current in the circuit? A says 12 amps, B says 8 amps, C says 10 amps, and D says 14 amps. Now if we listen to this question very well, it says we have 3 4 ohms resistors. So I have R1 to be 4 ohms, R2 to be 4 ohms, and then R3 to be 4 ohms. Now we have 3 4 ohms resistors, and these resistors are connected in parallel. So to look for the total resistance, we use the reciprocal. So the total resistance is 1 all over R is equal to 1 all over R1 plus 1 all over R2 plus 1 all over R3. So this is how we calculate the total resistance. So from here, 1 over R is equal to 1 over 4 plus 1 over 4 plus 1 over 4. And the total LCM here is 4, because we all have 4 as denominator. 4 divided by 4 multiplied by 1 is 1. We're simply going to add the top, plus 1 plus 1. And this is equal to 3 over 4. Now, this is 1 over R. So if we are looking for R, since 1 over R is equal to 3 over 4, then R is equal to the reciprocal of 3 over 4. So anytime I have 1 over something, if I'm going to look for that thing, I'm going to turn the other value upside down. So since I have 3 over 4 here, and it is equal to 1 over R, so R now is equal to 4 all over 3. If I remove this R, I'm going to turn it upside down. That is the reciprocal. So now this is the total resistance in here. Now I am asked to look for the total current, and the voltage is given to me V to be, the potential difference is given to me to be 16 volts. Now I know that V from Ohm's law is equal to IR, and I'm asked to look for the current. I'll simply divide both sides by R, so that my I is equal to V all over R. So my current here now is equal to the voltage given to me 16 divided by the resistance, which I have calculated to be 4 over 3. So we don't normally use two division signs to solve mathematics. I'm going to remove one and turn it to multiplication and reverse it also. So the current here is equal to 16. This division sign becomes times, and I'm going to turn this just like we did earlier there to be 3 all over 4. This is just the rule of mathematics. If I have two division sign, I will turn one into multiplication and then I'll times it by the reciprocal of the other one. It is a law. So now 4 can divide by 16. 16 can be divided by 4 to have 4, and 4 times 3 is 12. It is telling me that my current now is 12 amps. And this corresponds to option A in the question. So option A is the final answer. I hope that answers the question. Question number 39. Power supply is transmitted at a very high voltage and low current in order to A. Increase the power supply, B. Prevent overheating of the coil, C. Make it travel fast, D. Make it pass through the transformers. Now the reason why power supply is transmitted at a very high voltage but low current is because they want to prevent overheating of these coils that are carrying these currents. Now if they decide to increase it to a very high current, it is going to cause overheating. Thereby they bring down the current and then increase the voltage. And when they do that, the reason why this is done is so that these coils are not overheated, and when they become heated, they break down. So this makes option B to become the final answer. I hope that answers the question. Now question number 43. Question number 43 states, in an alternating current circuit at resonance, the angle of lead or lag is A. Pi degree over 2, B. 0 degree, C. Pi degree over 3, D. Pi degree. Now when we look at this, the answer is pretty straight. Option A, pi degree over 2, is actually the formula for finding the angle of lead or lag. I hope that answers the question. Question number 44. In Faraday's law of electrolysis, a graph of mass deposited against the quantity of electricity is plotted. The slope of the graph gives A. the electrochemical equivalent, B. the charge released, C. the current flowing, D. the energy released. So if we look at the graph, we're going to find out that at the base we have the quantity of the electricity that is passing through. We serve as C, the current flowing, and the energy all put together. And the correct option to this is the electrochemical equivalent, as we have seen from the graph. So the slope represents the electrochemical equivalent. I hope that answers the question. Question number 45. In a discharge tube, most of the gas is pumped out so that the electricity is conducted at A. steady voltage, B. low pressure, C. high pressure, D. low voltage. Now in this discharge tube, whenever these gas are pumped out, it's because they are trying to favor low pressure, and this makes B the final answer. I hope that answers the question. Question number 46. The radioisotope of uranium with mass number 235 and atomic number 92 decays by emitting 2 alpha particles, 3 beta particles, and a gamma ray. What is the mass and atomic numbers of the resulting daughter elements? Now this question is showing a decay of uranium, and this decay was said that we're going to put out the uranium like this with mass number 235 and atomic number 92. We said that it decay by emitting 3 alpha particles, 2 alpha particles, 3 beta particles, and 1 gamma ray. So now this substance decayed by emitting these particles. We have 2 alpha particles, 3 beta particles, and 1 gamma ray. So now we know the alpha particle is the helium atom, and helium atom has atomic number 2, mass number 4 for the alpha, and we're told that it emitted 2 alpha particles. These are the 2 alpha particles it emitted. And then secondly, it was said that it emitted 3 electrons, that is the beta particles. It's represented by electrons and then a gamma ray. So these are the emissions that were observed. So now what is going to be the resulting mass number and the atomic number of the daughter cell? Now we have this. So this is the mass number of uranium. The mass number is 235 and the atomic number is 92. So since we have this, we're going to subtract it from these two alpha particles here. We have 2 heliums, meaning mass number of 8, and we have atomic number of 4. So if I subtract 8 from this and I subtract 4 from this, I'm going to have approximately 227 and then 88 here. So now the mass number here is 227 and the atomic number is 88. Now it emitted also 3 beta particles, and the mass numbers here are 00, meaning the mass number is unaffected, but atomic number is 111. Since it is negative, it is going to be added to it, that is plus 3, so that this atomic number is now 91. So the gamma ray has no charge, no mass, so it is contributing nothing to this decay. So we are going to have the mass number now to be 227 and the atomic number to be 91. So since we have seen this actually corresponds to option A with atomic number 91 and mass number 227. I hope that answers the question. Now question number 48. Transistors are used for the A, conversion of AC to DC, B, conversion of DC to AC, C, amplification of signals, D, rectification of signals. Now option A, which is conversion of AC to DC, is actually done using a rectifier, and then conversion, which option B, which is conversion of DC to AC, is actually done using an inverter, and C, which is the right answer, transistors are used for the amplification of signals, which is the right answer. And AC actually stands for alternating current, and DC stands for direct current. Most students make mistakes of calling it air conditioner, but it's actually alternating current. I believe that answers the question. Question number 49. A typical transistor characteristics is represented as, and now we have seen the various graph which is plotted current against voltage. We see the graph didn't start from the origin, it is actually a falling graph. We saw option B, which is a curved graph, option C, which is a straight line graph starting from the origin, current against voltage also, and then option D, which is a curved graph curving inward, and then option C here is the final answer, because it typically depicts a typical transistor characteristics. I hope that answers the question. Question number 15. Which of the following is a pure semiconductor? A, silicon, B, phosphorus, C, transistor, D, carbon. Now we have two major types of semiconductors. Now semiconductors are substances that can conduct electricity sometimes under some condition, and under some condition they don't conduct. So they serve as a bridge between conductors and insulators. Now conductors are those substances that allow electricity and heat to pass through them, and then insulators do not allow. Now in between these two live the semiconductors. Conductors, and these semiconductors are divided into two. We have the intrinsic semiconductor, or the I-type, the intrinsic, and we have the extrinsic semiconductors. So we have the intrinsic semiconductors and we have the extrinsic semiconductors. Now these intrinsic semiconductors are very, very pure, while these extrinsic are impure. Now these extrinsic semiconductors have been doped with some elements to further their conductivity, while the intrinsic semiconductors are very, very pure. An example of an element here is silicon. Now, silicon is an example of a pure intrinsic semiconductor, and which actually matches with option A here from the question, which of the following is a pure semiconductor? Pure semiconductors are intrinsic semiconductors. An example of a member here is silicon. I hope that answers the question. We thank you for staying with us as we've come to the end of Physics 2010 JAMB question, and we really appreciate your effort for being to it. You allowed to stream a particular video as much as you can so that you get used to this question. Repetition is one of the most important key in understanding. When you watch this video, you watch it over and over again before you know these questions, and the solutions we will be given will be part of you for life. So we really appreciate you, and we urge you to subscribe to our channel if you haven't. Click on the notification bell so that you'll be the first to get our videos immediately they come your way. Thank you so much for being part of this.